La 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 la. Alright, hopefully I'm recording. So, what I'm going to do here is show you the derivations for the three common Gauss's law problems, or the three things that you have to, really the three things you have to be able to use Gauss's law to derive the electric field for. So, first, we are going to do a sphere of radius capital R with a charge of Q on it. So actually this is more like a spherical shell. So you might say charge of Q on the outer surface. Okay, good enough. Alright, so let me see if I can draw this. Let's see, where do I want to draw this? I will draw this out here. Yeah. Capital R. Okay, and the charge is Q. Might be positive, might be negative. We want to find the electric field at a position R vector. Okay, now that R vector, let me draw that in some other color, like, oh, how about lavender? That's totally an R vector color. So R vector here might be greater than R, it might be less than R, or less than capital R. What I mean is the magnitude of R vector might be greater than capital R, might be less than capital R. We might be outside of the sphere, we might be inside the sphere. Who knows? Well, we want to solve for both cases. Okay, so the first thing you do is you apply symmetry. So let me just go ahead and do, we'll do solutions in blue. Why not? Yes, I'm way too interested in colors. So first you can say, by symmetry, the electric field has to point either, so this is your point you're interested in, has to point either straight outward or straight inward there. And symmetry is the idea that the universe should not prefer one coordinate frame to another. So if you imagine you are outside of the sphere somewhere, you don't have any sense of direction except for what's towards the sphere and what's away from the sphere. You can't talk about what's left because that implies that you know something about which direction you are facing or which direction is up. You can't talk about which direction is right. Or anything. All you can talk about is towards the sphere and away from the sphere. So by symmetry, the electric field has to be either point towards the sphere or away from the sphere. And what I'm going to do to represent that is I'm going to say the electric field has to be equal to a scalar times r hat. The scalar E here could be positive, could be negative. So it's not a magnitude necessarily, could be a negative number, but it's some, it's just some scalar number that has to, and it's the strength of the field, but the field has to point either in the r hat direction. So remember, r hat is a unit vector that points the same direction as r. So r hat points outward and has a magnitude of 1. The electric field has to either point that way if capital E is positive, or point towards the center of the sphere if capital E is negative. No other options. I'm going to say, just for the sake of having something to fill in, that it goes outward, and if we solve it and we get a negative number for capital E, then we know we guessed wrong and it goes inward, but it should still work. The second thing is, also by symmetry, and I'm just going to go ahead and put all my symmetry as one step. Also by symmetry, the electric field magnitude has to be the same as long as you're at the same distance from the center. So if you are right here, for example, your magnitude of your electric field will point this way, right? But the magnitude can't be different here than it is here, provided this is at the same distance from the center as this guy. So by symmetry, we can say that the magnitude of the electric field can depend only on scalar r, which is equal to the magnitude of your r vector. So at any given point, the magnitude of your electric field has to be determined by your distance from the center of the sphere. Like down here, for example, if you're at the same distance, it's got to be the same magnitude as it is here and here. Okay? The magnitude is determined by that distance, and the direction also. Or, sorry, not the direction. Well, the positive and negativeness of the direction. But the direction is always going to be pointing either outward or inward, and it's got to have the same magnitude at the same distance r. So this is r, and this is r, then these all have to have the same magnitude. Okay, even though I've written the vectors different. This is not, what is that? Okay, I don't know. That's just like random saving. Sorry. Anyway, so that takes care of sort of setting up as much as we can by symmetry. Now at this point, we have to actually construct a Gaussian surface. Okay, so I'm going to do my Gaussian surface in green for Gauss. Okay, my Gaussian surface, I want to find a surface, remember, where the electric field always is perpendicular to the surface, or where it's parallel to the surface, because those are my nicest ones. So my Gaussian surface, so 2, let's say my Gaussian surface, and I'm sort of trying to, well, I'm actually trying to not explain so much and just go through the steps. I'm sort of assuming you understand the whys, although I did spend a lot of time just talking about symmetry, but whatever. So my Gaussian surface here is going to be a sphere of radius little r. Important to keep the Gaussian surface separate, keep the idea separate from the sphere. So sorry, you want to keep the Gaussian surface separate from the solid object surface. So capital R is the radius of this physical sphere that has the charge on it, and little r is the radius of this Gaussian sphere, which is just a sort of an abstract concept. It's not a real object. It's just a geometrical, you know, thing. Okay. So what we can do then is we can say also, we can say the normal vector for the sphere, the surface normal vector. So this is a vector on the surface that points straight outward. The normal vector for the surface is equal to n hat, the unit normal vector is equal to r hat at all points on this. Oh, geez, stop it. Okay. At all points on the sphere. Okay? Or so on, I might say on this sphere. Okay? So, E-R-E, there we go. So, at any point you go to, your r hat vector and your normal vector, your unit normal vector, will be the same thing. And that's important because that lets us, make things easier in the next step. So, I'm going to just stick with, I don't know, what's a good color? Oh, red. Okay. So, step 3 is that the total flux through the surface of the sphere is equal to the area of the sphere, surface area of the sphere, times this dot product, E dot n hat. Okay? And E dot n hat, okay, is, remember we defined, we said that we know the electric field must point outward or inward, so E, we said this on the other page, is equal to E times r hat. So this here, this E dot n hat, is equal to E r hat dot n hat, and r hat and n hat are the same thing, right? So they're the same thing, they're unit vector. You take a unit vector and dot it with itself, you get 1. So that's just equal to E. So we can say then that phi sub E equals A times E. Now if you want to do this formally, your teacher may say that you actually have to say this. Your teacher may make you do this. Electric flux is equal to the integral of E dot n hat dA. And he's talking about a surface integral. I don't know if he wants you to do that or what. He's the one who's going to be grading, so that's your lookout. But he may want you to do that, in which case you just write that, and then you end up saying that that's equal to A times E dot n hat, since this is a constant. Or really what you say is equal to E dot n hat integral over the entire surface. Okay, and since this is constant, you can pull it out of the integral, and so then that's just going to equal this here. Okay, so there you go. So that is the entire. This is the entire flux out of that sphere. So A here is the surface area of the sphere, and E is the electric field on the surface, or the magnitude of it plus or minus if it's going, depending on whether it's going in or out. Okay. So now the area of the sphere, Well, the surface area of a sphere is 4 pi r squared. Remember, this is a sphere of radius little r. So, therefore, our entire flux is equal to, let's see if we can do that better, 4 pi r squared times the electric field on the surface. Okay, so now we found the total flux through the surface, and this electric field here might vary with little r. Okay, so this electric field here could be a function of little r, but it can't vary with anything else. We know that. Okay, so now, oh gosh, oh geez, baby blue. Okay, so now the next step, and I'm just going to go ahead and make another page for this, is to actually apply Gauss's law, which says that the total electric flux out of the sphere, or out of any closed surface, is equal to, yikes, equal to the charge enclosed divided by epsilon naught. Okay, so if we take our electric flux expression from the previous page, 4 pi r squared times the electric field on the surface. So again, this is area, in fact we can just put parentheses around this. This is the surface area of the sphere, this is the electric field on the surface. We're finding the flux out of the surface. Okay, is equal to, well, Q enclosed, if we back up a couple, Q enclosed is the total charge enclosed in this Gaussian surface. Okay, and we said there's a charge Q on the outer surface of this sphere of radius r, this little one. So the total charge enclosed is just that capital Q. So I can't believe it takes time to load this stuff. Okay, so capital Q over epsilon naught. Okay, the next step then is we want to find the electric field, right? So I'm going to pull this 4 pi r squared over to the right, and it's going to be Q over 4 pi r squared epsilon naught. And so the customary way to write this is, of course, E equals 1 over 4 pi epsilon naught times Q over r squared. And then this is the scalar. Remember, we determined that the direction of the electric field is either out or in, okay? And it's this times r hat, right? So formally, to get a vector for the electric field, we need to multiply the r hat back in. So 1 over 4 pi epsilon naught, okay, times Q over r squared times r hat. Or, and I will just do this, is we can turn the 1 over 4 pi epsilon naught into k, which is more convenient for this one. Okay, generally more convenient. So there you go. And wait, there was an assumption I made here. This is true if the, well, I'll tell you what, let me show you. So the way I drew this, my Gaussian sphere with radius little r is bigger than the charged sphere, right? So because the Gaussian sphere is bigger, it contains the charge capital Q, which is on the outer surface of the sphere. So remember, the capital Q charge is on the outer surface of this solid sphere, right? These little blue dots I'm drawing are where the capital Q charge is. They're inside the Gaussian sphere, or it's inside the Gaussian sphere if the Gaussian sphere is bigger than the solid sphere. So if little r is bigger than big R, I know that sounds a little confusing, but let me just, okay. And so these are true if little r is greater than big R, okay? Otherwise, and so I'm going to solve for if little r is less than big R, and don't worry so much about if little r equals big R. That's kind of a weird case, okay? But if little r is less than big R, then, and I'm going to do that just in this little area here, then Q enclosed equals 0. And the way to see that is to go back and say, okay, suppose little r is less than big R, then my Gaussian surface is in here, because the radius of it is less than the radius of the solid sphere. And so it does not contain any of the charge, because this charge Q is on the outer surface. So if little r is less than big R, you're inside the sphere, and you're not containing anything in your Gaussian sphere. So that means then that the electric flux through the sphere must be 0, and all the other symmetry rules apply. In fact, all the symmetry we did applies. But if you look up here, this is going to be equal to 0 because because Q enclosed is 0. And so that's going to be 4 pi 4 pi r squared epsilon naught, okay? And what that means, oh, so I'm sorry, no, not 4 pi r squared epsilon naught, it's 4 pi r squared, come on, back up, times E. And so what that means then is that in order for this to be equal to 0, something over here has to be equal to 0. Well, r isn't 0, generally, pi isn't 0, 4 isn't 0, so it must be E. Now, I suppose this does raise the question of, well, what if you are actually looking at the point at the center of the sphere, so r equals 0? Doesn't that mean then that E could not be 0 and still satisfy this? And honestly, I don't know if there's a really satisfactory answer to that, but whatever. So, point is, the electric field is 0, and actually that means the electric field as a vector is 0, if you are inside the surface of this charged sphere. So to review, we have a sphere of radius capital R with a charge capital Q on the surface of this charged sphere, okay? The electric field around it is either this or this, whichever one you prefer, if you are outside of the sphere. If you are inside the charged sphere, so you're sort of underneath the charge, as it were, the electric field there is 0. It's really just shell theorem again. Okay, anyway, that's the complete proof for, or the complete derivation for electric field due to a charged sphere or sphere of charge.